Hello students, welcome to Unit 1, Lesson 3 on temperature and heat. Today's lesson, we're going to look at 4 objectives: define latent heat diffusion and define latent heat vaporization. And we'll relate heat and change of phase and perform calculations based on calorimetry. The latent heat diffusion describes the amount of energy needed to change 1 kilogram of a material from solid to liquid or liquid to solid. So as we see here in the diagram, we have the 3 states of solid, liquid, and gas. And latent heat diffusion is looking at one of 2 processes. Of course, we would look at freezing if it was going this way and melting going this way. Now, if it's freezing, the substance that's undergoing freezing, well, it's losing thermal energy, all right? And if it's melting, it's gaining thermal energy. So the freeze is a loss and the melt is a gain, all right? Now, the latent heat of vaporization describes the amount of energy needed to change 1 kilogram of material from liquid to gas or gas to liquid. So what we're looking at in this diagram in this case is going from liquid to gas or vice versa. So if it's evaporating, if it's going up in this direction, of course that would be a gain of thermal energy into the substance. And if it's condensing, if it's going from a gas to a liquid, of course that would equate to a loss of thermal energy in the substance. Let's have a look at our formula that we'll be using to talk about the heat flow. So the amount of heat needed to change the phase of material depends on the mass and a value L of latent heat. Now you have to be careful. You have to look at the situation and make sure you're understanding what phase change is occurring. Based on the phase change, that will help you determine the value that you'll take from this table. And this table looks at a number of different substances here. You know, if we just take water as our go-to example, we know the melting point of water is 0 degrees. Now, the latent heat of fusion for water, when it comes to trying to melt ice, we need 33.5 times 10 to the 4 joules for each kilo. Now, if then we increase its temperature to the boiling point and we want to change that kilo of water to steam, well, now that it's at the boiling point, 100 degrees Celsius, we would need to add 22.6 times 10 to the 5 joules of energy per kilo. You'll notice that it takes a lot more energy to have something vaporize versus to have something melt. Here's a visual depiction, a graph showing us the entire process of taking cold ice at -30 and turning it into water vapor. Okay, so let's just have a look at this. On this axis here we have temperature. So it starts at -30. Now, before we can melt ice, we need to bring the temperature from -30 up to 0. So it only requires a little bit of energy there to do that. All right, so it's only this much energy. Now that it's at 0, we can melt it, and it requires this much energy here. Okay, so there's a significant amount of more energy to melt the ice than there was to bring its temperature up to 0. Now, if we go from 0 up to 100, of course, that requires about this much energy, which is more than melting it in this case, because it only started at -30. And now just take a look at this. If we want to take that water and we want to change it from a liquid to a gas, it requires a very significant amount of energy. Okay, so when we look at our table, that's why we have a whole factor to the 5 versus to the 4. 4 is for fusion, melting, and this 5 here is for vaporization, for evaporating. Let's take a look at a worked example here. So if we have ice and it's placed in a styrofoam cup, now you've seen these in the lab by now, okay? The calorimetry little styrofoam cup. So if we put it in something like that, containing 0.32 kilograms of lemonade at 27 degrees Celsius, The specific heat capacity of lemonade is about the same as water, so we'll use the C value of water for lemonade. After the ice and lemonade reach equilibrium temperature, some ice still remains. Okay, so assume that the mass of the cup is so small that it absorbs a negligible amount of heat. So we're going to pretend there's no other heat loss here. Let's take a look at how we'll equate our gain and our loss here. So when it comes to melting ice, again, when it comes to the melting process, it's a gain. And of course, that lemonade was the donor. The liquid lemonade donated that thermal energy. Okay, it heated that ice and melted it. So on this side, this is our loss, and on this side, this is our gain. If we continue on looking at the Q value for gain and the Q value for loss, well, Q equals mL for the melting of the ice, and the Q value for the change in the temperature of the lemonade is Cm delta T. Remember, we're using the C value for water here. It's the mass of the lemonade and that change in temperature that occurred for the lemonade. And for M here, we have the mass of the ice that gets melted under the value of L for latent heat of fusion. So the only value here that we don't know is M. We just bring L over to the other side, all right? And it's down here in our denominator. And we plug our values in. C for water, same as lemonade. The mass of the lemonade. The change in temperature went from 27 and of course down to 0, which is the melting point. That would be the final temperature. And this here, students, is one of those implicit or hidden pieces of information in the question. Okay, so you needed to be able to understand that the final resting equilibrium temperature would have been 0 because it's the melting point. Finally, we plug in our value here, the latent heat of fusion for water, and when we calculate, we find that we have melted 0.11 kilograms of ice. It's now time to continue on to the learning activities. Thank you for your time.